Hello and welcome to the Geometry of Parabolas. And so today we're going to look at parabolas and why parabolas and quadratics in general get a bad rap. A lot of students groan and moan when you mention quadratics, but they're actually pretty cool. So a definition of a parabola. Here's a quick definition. It's a set of points equidistant from a fixed point called the focus and a fixed line called the directrix, whatever that means. A directrix is just a line. So here's a directrix right here, this green line. And then you have a point we'll just call the focus. Now when we say fixed point and fixed line, that means that these don't move. So if these are fixed in space, then what is all the set of points that are the same distance, equidistant to both the directrix and the focus? Those points form a parabola. This diagram right here takes one particular point P, and if we were to measure the distance from this point to the focus and this point to the directrix, those two distances will be equal. And that will happen for any point on a parabola. One thing to remember when you're measuring the distance from a point to a line, you always measure at a right angle. But you know, we can kind of eyeball it. Even if I took this point on the parabola, the distance from this point to the focus and this point to the directrix, they do appear to be the same. If you take a look at all those points form what's called a parabola. Let's investigate this idea a little bit more. And we're going to use GeoGebra to do this. So GeoGebra is just a free website, geogebra.org, and as the name implies, it takes geometry and algebra and blends them together. It's actually a really cool tool. I'm going to go ahead and say, start the calculator. And it always defaults here. I actually don't care about the grid, so I'm going to go over here to the settings gear. I'm going to turn off the axes, the grid, and I also don't want to snap to grid. So I have a nice blank canvas here, and I'm going to go ahead and use the geometry tools. So I'm going to click on geometry, and we're going to create a parabola using that definition. So it was a set of points equidistant to a fixed line, the directrix, and a fixed point, the focus. I'm going to start with a line and a point. So I'll go ahead and choose point here, and then just click on point. And then I can go over here to get the arrow. I can move this point around if I want. I'm going to go ahead and change the name of this to focus. That way we know where the focus is. I'm going to scroll down to lines, and I'm going to go ahead and choose line. And lines are defined by 2 points, so I click one place and click a second place, and there I have a line. And it defaulted to calling this line F. I could go up here to click on this arrow again, move, but I'm just going to hit the escape key. Notice it automatically selected move. Let's change that name to directrix. And then I'm going to do one more thing really quickly. I'm going to create another point, and I'm going to put this point on the line. Now I want to take a look at what we've got so far. I have a focus. Notice this point freely moves around anywhere I want. I have this line, the directrix. I can move that around. And because this line was defined by points A and B, if I move point A or point B, it will also move those around. Point C, though, was placed on the line, so I can't move C anywhere I want. I can move it anywhere on the line, though. So this is one of the cool things about GeoGebra, is you can create these structures like this. Okay, so now how am I going to create the set of points equidistant to the directrix and the focus? I'm going to use a little bit of the geometry tools that we've learned previously. To do that, the first thing I'm going to do is I'm going to create a perpendicular line through point C that's perpendicular to the directrix. Scroll down to construct perpendicular line. I select the line and the point. And so now, as I move point C around, that perpendicular line moves around with it. And even as I move the line around, notice my perpendicular line stays perpendicular. Okay, so how does that help us? Don't worry, I'm getting there. I'm going to create a line segment that connects point C to the focus. So I'm going to go back on here to lines, to segment, and create a segment. Wherever I move that focus, that remains a segment where the focus is one of the endpoints. And then I'm going to create a perpendicular bisector to this segment. I'm going to go back to construct and do perpendicular bisector, select the segment, and then I'm going to go put a point at this point of intersection. What did I just do? Can you, again, think about this from what we've done in geometry lately. What can you tell me about point D given the fact that it's on a perpendicular bisector? Do you remember a theorem that we had? Pause the video and see if you can remember. All right, hopefully you did pause the video. And remember, we had a theorem that said any point on a perpendicular bisector is equidistant to the endpoints of the segment. And so point D is equidistant to point C and the focus. And since C is also on a perpendicular line to the directrix, we know that this particular line segment represents the distance from point D to the directrix. So point D is equidistant to the focus and the directrix. Point D lies on my parabola. And as I move point C around, this distance to the directrix and this distance to the focus remain equal. Now just focus on point D as I drag C along this directrix. Can you see how D is going in what looks like a U shape? Kind of looks like it's making that parabola. And it is. It's hard to see though. So let's do a little bit more to this picture so we can see it. First of all, I don't need, whoops, I didn't want that. I don't need this line segment. I'm going to scroll right here where it says show hide object. I'm going to click on the line segment and hide that. And I'm going to click on this perpendicular line and hide that. So now those are hidden. They're still there. As I move point C, we can see D moving around. I'm leaving this line right here for a reason. And in fact, point E, let's just get rid of point E. That was an extra line. Now the other thing that I do want to do, let's get those segments back, those equidistant segments. So I'm going to go to line, create this segment and this segment. And let's make these red and a little thicker. Red and a little thicker. Gives us something to focus on. And we can see those do appear to be equal. And if I even go to measure, I can click on distance or length and select this line segment and this line segment, and you can see that those are equal values. And as I drag point C around, those values change but remain equal to each other. So D really is on the parabola, according to our definition. The last thing that I'm going to do to actually be able to see the parabola, this is a really easy thing. If I click on D, click on these 3 points, I can say show trace. And notice I have a parabola. Ta-da! And if I move the focus closer to the directrix, notice it makes the parabola skinnier. If I move the focus further away, it makes the parabola wider. So that's how we can construct it. Now, because of this, we have some really powerful stuff. This line right here represents the tangent. In fact, actually, let me just clean this up a little bit here. This line represents the tangent to the parabola. And if you were to measure the angle of anything coming straight into the parabola, it would bounce right off into the focus. And that's a cool feature of a parabola. So let's just look quickly at some uses for parabolas. I'm going to go back here to the slideshow. So this is what I was talking about right here. You can actually have, like, if you think of a flashlight or those big spotlights that you see that shine the big beam in the sky, like the Batman signal, they create such a straight beam because those reflectors behind them are parabolic. Imagine a light bulb was right here. It shines the beam, and no matter where it hits on the reflector, those beams automatically go straight out. And that's what makes that beam so focused. If you think of a telescope design, now there's lots of different telescope designs, but one possible telescope design, the light comes into the mirror, and then we have this parabolic mirror, and then you have this secondary mirror right here, and it all bounces these light rays to the secondary mirror, which then goes here to where your eyepiece would be. This is a parabolic mirror right there. Satellite dishes, same kind of thing. Whoops. Sorry about that. Satellite dishes, they have the same kind of structure here. This bowl right here is in the shape of a parabola. If you spin a parabola on its vertex and it makes a paraboloid. The reason why it's so important that you aim your satellite dish is because all the signals that come straight in at a right angle to the directrix will bounce right here, which is located at the focus. And then if you've ever seen in, like sometimes they show it in TV shows or movies, somebody's trying to listen through a wall. And how do they do that? A lot of times they're holding something that looks like this. It actually does work to some extent. What happens is this is in the shape of a parabola, and so the sound waves that come straight in, that's why they aim it right at where the person's talking. The sound waves that come straight in go right here to a receiver, which then is amplified and sent to the headphones. So it's pretty cool. Parabolas have a lot of uses, and a lot of people don't give them enough credit. Now, going back to mirrors for a moment, I'm just going to kind of leave you with this food for thought, because we've also talked about ellipses and hyperbolas and what those definitions are. Just, if you want to think about it, we'll discuss this in class next time. Think about if we actually had a mirror reflector shaped like an ellipse. What's going on in here in this picture? And then a hyperbola. If these reflectors, this reflector is shaped like a hyperbola, but these are shaped like parabolas, can you imagine what's happening as far as the foci and the shape of the reflectors and the geometry of everything involved? Parabolas and conic sections in general have a lot of uses in optics and acoustics. It's pretty cool. Anyway, this food for thought I'll leave you with, and I'll see you in class. Bye-bye.